Okay, last week I started on observer that we use that word basically to mean the same as an estimator, except when you do controller design, then they use another word called observer, is to use this equation 55 now. So K here is, I change it to KOB just to keep in line with the term that they use when they do model predictive control. And we use this equation to estimate X hat. Now, I told you before when I teach command filter, you look at this equation, X is called the true state. We think of the temperature inside your body. It's not practical to measure all the time. Y is a temperature you get when you use a temperature gun. So we measure Y, and then, but what we really want is the temperature inside your body, the X. So in manufacturing, it's the same. You cannot measure the temperature of your wafer because all the chemicals are on it, and you want to make what 3 nanometer, 4 nanometer critical dimension. You go and touch it, you spoil everything. So all you can do is possibly measure temperature elsewhere. Temperature of the oven, of the bake plate, of all the instruments, and then from there you estimate X hat. Estimate X or X hat. And it's really the X that you want to control, the temperature on the wafer, not the temperature of the oven. All right, so we use this and we call it the observer when it's used together with control. And when we use command filter to do the observer, we use the steady state command filter. I showed you before that if you iterate this, at first, K will change. Then after a few iterations, K will reach a constant value. So we use the constant value. In fact, not only K, P will also reach a constant value. All right, so we will then use X hat as the estimate of the true state. So now which means now then we'll go back to look at the model predictive control algorithm. All right, so now this is the model predictive control algorithm that is given in 29. Over there at 29, this is actually X, which means when we learn model predictive control, we assume that, oh, I actually can measure the temperature of the wafer itself. All right, in practice, you can't. So now we will replace X with X hat. All right, here is stated X is now replaced by X hat. And X hat is obtained from the command filter that I just showed you just now, this one, 55. All right. In the Kalman filter, this was U. Since now the input to model predictive control is delta U, so we change U to delta U. It's just the input, all right? In Kalman filter, we call the input U. In model predictive control, we call the input delta U, so we just change it to delta U. Now, so that was Kalman filter. There's another popular way of designing observer, that's to use pole placement. So this is another method to design your KOB. Previously, I used Kalman filter to get my KOB, and I make it to be equals to the K in 55 when it reached steady state. All right, so there's method 1 or Kalman filter method. Now we discuss pole placement method. These are quite standard in state space control. So, but yeah, I teach it in the context of model predictive control. So now you just take the error between what you estimate and what is the true state, you will get this. All right, I tell you what to do already. Subtract 22.5 and then take 2.6, put inside here, and then you will get this. Okay, now, then after that, you call the difference between what you estimate and what is true as the estimation error, X tilde. So if you take this one also X tilde, then this will be here. All right. Then after that, you rewrite, you will get this thing here. This will also give you this X tilde. Okay. Then you factorize, you will get this. After that, here you see, this is the estimation error. Means what? You estimate X hat. This is the true value. So what you really want is your estimate to be equals to your true value. That means you want X tilde to be equals to 0. That means that what you estimate is equals to what is true. All right. So from this equation, you can easily see that since KOB is the gain, observer gain that you choose, we can always choose KOB such that whatever is the initial error, all right, if you think of scalar, A is given is the plant, C part of the plant. You can always choose KOB such that this is less than 1, so that after a few sample, K sample, whatever initial estimation error, finally it will be 0. Because if this is less than 1, you multiply to the power of a few K, a large K, then this whole thing will become 0. So obviously K can be chosen such that you can have it determines the convergence rate to 0. All right, so by simply saying this one So you can see it's obvious. This one is K. If you don't know what I'm talking about, is X tilde 1. Then after that, X tilde 2 will be equals to X tilde 1. But this one, you can put this thing inside here. Then this will be equals to, you see? So likewise, if you do some more, you will see X tilde 3 will be equals to, okay, so if you choose whatever KOB such that the what is inside the bracket, if you just think of scalar to be less than 1, then for large K here, you will get 0 over this side. Even though your initial error is large, which means initially your guess between the real wafer temperature and the temperature that you estimate is large. After a while, they will converge and the estimation error will be 0. Okay, so from there you can see. Now, typically, they will choose the poles. All right, they will choose the poles. So from this equation, if you take the Z transform, this one, you can write it down as this. Okay, and Z transform of this, you will get this. You reorganize everything, you get this. Then after that, X tilde will be just equals to this. Okay, if some of you are not comfortable with matrices, then this one, if you look at this equation and think of all these as scalar, then you will be able to write X. Okay, and then you choose KOB such that how you choose KOB, you equate this to 0. So that will be the poles. And then if you have stable pole, you know that stable transfer function, then your X will finally decay to 0. All right. So since it is matrices, instead of just equating to 0, you equate the determinant to 0. So these are equivalent. All right. So like I said before, this now is then replaced by X hat that you obtain from the observer. So how do you choose KOB? We now look at since we have this, we substitute into the plant. All right, this is typically inside the plant transfer function. This is delta U. So you substitute inside. All right, you substitute inside. Then again, since there's an X hat here, you put X hat, replace it with X tilde. So you put this, replaced by this inside here. Then you rewrite, you'll get this. Now, so there's an equation 4.1, which is X. So this equation now you write in matrix form, which is this row here. And then 37, you write in matrix form, this should be this row here. All right, you go and look at 37. Is this one? X tilde A minus KOBC. So is X tilde A minus KOBC. All right, times X tilde. So these two equations will then give you this matrix. Now, you find the poles again. There's a formula. You go and find the transfer function y over r and then equate the denominator to 0. So typically, we call these what? F, let's say this is G, this is H. Then the formula is H ZI minus F times G. All right, inverse. If you treat all this as scalar, then it's easy for you to see that this is nothing but HG over Z minus F. And then to find the pole, you equate the denominator to 0. All right. But all this, if they are not scalar, then all you need to do is just equate the determinant of this. All right, this is F. So it's just Z minus F. So these two are equivalent. All right. So you equate the determinant to 0. If it's scalar, you just equate it to 0, the denominator. Then you will get the closed loop poles. And if you do the maths for this determinant, I can't teach determinant anymore. You find that this determinant is equals to 2 determinant multiplied together. And then this, since it's equal to 0, you can then break down into 2 pieces, which means equate this to 0 and then equate this to 0. Okay, that is algebra. And then you will see, hey, if I equate this to 0, that was the same as $35. All right, this is the same as 35. And 35 is when I first teach the model predictive control, assuming that I know the true temperature of the wafer. So now you can design your model predictive control and get K MPC, assuming that you know the true temperature of the wafer. It doesn't matter because your final closed loop pole, the pole are not affected when you use a estimator. It is still the same. Even though here you use an estimator, you still use this equation to get the closed loop poles. Just like when I taught you without using estimator, you get the same closed loop pole. Now I teach you to use the estimator, you also get the same closed loop pole. So you don't have to worry that later on you don't have the true measurement, you don't have X and you have to use an estimator. You don't have to worry because later on you get the same closed loop pole. Your original design is not changed. All right, so this is what it is saying. Then this you look is the observer, which means 38. So here shows that you can design the controller assuming that you know all the states accurately without using the estimator. Then you go and design the estimator. Choose this, which is 38. So you choose 38, which we discussed before, 38 over here. And this, if you think back, it is this one. It determines how fast you converge from your initial error of estimation to the time whereby your estimation is equals to the true value. Your KOB determines the convergence rate, because by choosing KOB, this bracket here will be less than 1. The smaller this bracket is, the faster this will converge to 0. And so KOB determines how fast your estimator will converge to the true state. So which means now your controller design, you can do it in 2 steps. Do the controller design, then do the estimator design. They don't affect each other. The estimator design do not affect the controller design, because the controller design poles are unchanged. Okay. Now, so I've taught you 2 ways of doing an observer. So the last comment is, obviously the Kalman filter way allow you more interpretation. Kalman filter way not only allow you to finally know where is the closed loop poles of your observer, which means how fast you KOB. Once you know KOB, you can easily calculate the poles here, the poles here or here, and that tell you how fast it converge to the true value you estimate. But on top of that, because you use R1 and R2, that also give you an interpretation of how much you trust the process model or how much you trust your measurement. So you understand the observer design better. You have more interpretation than if you don't use a Kalman filter. Though both end up is the same observer, but because if you use the Kalman filter approach, you have extra interpretation of R1 and R2. Okay, we'll see the tutorial question later on. Okay, let's look at the tutorial question. Okay, I will not teach question 4 in the tutorial, because I think this question is confusing, so I will not go through it. You don't have to go through tutorial. You don't have to look at Q4. All right. So let's look at Q5. Okay, so Q5, assume that the states in example 7 is not measurable. Example 7 was an MPC problem, and we assume that we know X, which means we know the temperature of the wafer. All right, now we assume that we don't know. So in example Q5, we actually got this. Sorry, example 7, we got this. In example 7, the plant was given like that. All right, this was example 7. Oh, yeah. Before I forget, the university say next Friday is a holiday, so there's no lesson next Friday. Don't come here. All right, next Friday lesson is cancelled. All right, so now we are supposed to use the Kalman filter to estimate X hat. Because I need to use the Kalman filter, I have to invent R1 and R2. So this is my invention. It's not there, but I invent it. Okay, so now I invented this. So I now say, hey, the whole process looks like that. This one and this one are invented. All right, and this is the Kalman filter model. Okay, so let's say I invent all this, all the W and all the V. So I put some numbers inside. V, the variance is 0.1. R1 is 100. Okay, then A, to verify that the steady state Kalman filter basically gain is KOB is this one and POB is this one. All right, this is easy. All you need to do, we look at the solution, take these two matrices, go into the Kalman filter equation. Go inside 55, take the KOB, all right, where is, K is now called KOB. So the P and the K, if I substitute the value here, I get the K value here. All right. And if I substitute the K value here and the P value here, I get back the same P value. So you see that, oh, they are at steady state, which means the PK minus 1, I get the same value for PK plus 1. So that is steady state. All right. Likewise, here, if I get the P here, I still get back the same K. So no matter, since all the P is the same, when I put here, I get the same P here. Whatever P I get here, I'll get back the same K. So basically, you verified that your K and your KOB and your POB have reached steady state, right? In practice, all you need to do, iterate until you use a MATLAB, go iterate until you see that, hey, K never change, P never change, then that's it. That will be your KOB. All right, it's as simple as that. Okay, so I say that substitute this into this and this on the right side, then give the KOB and POB on the left side. So right side, left side always give you the same number, so you converge. So B, what is B? So initially, you think that your initial X hat is minus 0.1, minus 0.1, but actually the real X is 0, 0. So now which means initially you guessed wrongly. All right, it is supposed to be the true state is 0, 0. You guess is minus 0.1, minus 0.1. So now you have to use what you guess to calculate the MPC delta U, and then find what is Y for K equal to 0, 1, and 2. So now let's look at the solution. So like now, you can only use what you guess because you don't know what is the real one. So you will use the observer, which is this one. All right, KOB is already given to you. And then after that, all this equation, 40 will give you delta U, 2.5 is X, 2.6 is Y, 4.21 is X hat K1. So you have to use those. So at K equal to 0, this is Y is this. Okay, Y is this. And since this is given as this, so this is here. C is this one. So Y is 0 when you start from the beginning. Then this is your MPC. All right, KR was calculated in example 7. Is it example 7? Yeah, I think I said this was taken from, yeah, example 7. So the KR, this is example 7. All right, this is also example 7. Go and look at example 7. We calculated KR and KMPC is this. Now in example 7, R is 1, so R is a set point. This is 1, so this is clear. In example 7, we use the real X, which then is 0, 0. But now we guessed wrongly, so we guess is minus 0.1, minus 0.1, so we put that inside there. Okay, then you will get this. Example 7, you will find that this is 0, 0, you get a different number. So now your delta U is different from example 7. So at K equals to 1, your new true state will be equals to this. Since you calculated your delta U to be this, you have to stick that inside here. Okay, you look at example 7, this is A. This is the true state, it is this one. This is given as this. All right, so your true state is 0.607. Then your output will be this. So you stick that in here and here. So we go through one more example. Then now X1, you will have to take this is what you guess. So you stick it inside here. This was calculated previously, which is here. All right. This is KOB. This is Y, C. This is what you guess. So you guess wrongly. You calculated. This is your new guess, your new estimate, and you have to put that inside here, which then is here. Okay. And then your new delta U1, which is different from example 7 because you are using your X hat. Okay, you can continue to iterate and check the numbers. I will not go through because they are the same steps. Okay, C. What is C? C, what is question C? Okay, use the closed loop equation to find k equals to 0, 1, 2, 3. All right, closed loop equation. You go and look at your closed loop equation, which is 42. Let's see, the closed loop equation is 42. Okay, this is the one. Because now you are talking about you are having an observer, so you use this closed loop equation whereby your observer is included in the closed loop. All right, it's included in the whole control loop, it's inside. So you have to use this one. So if you look at equation 42, you write down what is this, what is this, what is this. Okay, then you go and find what is y over r, which is this. All right, so we go and look at the answer. Okay, 42. I apologize in 42. That time I just now I anyhow write, I just put this F, this is G, this is H. So here I put AF, BF, and CF. They are the same thing. All right. Just now I just scribble, I put F, G, and H. So X hat in 42 looks like that. So now you stick things in. X tilde is the estimation error. So you put the true state minus the estimate. This is the estimation error. So true state is this one. This one we say is this one. All right, at k equal to 0. So X F at k equal to 0 will be 0.1.100. Okay, then just now I call F. Here I call AF. You go and look, F is this formula. You go and stick in what's all the number inside, you will get this. All right, and you have to stick it in yourself. This one, just now, I wrote it as G is this one. So you stick in the number, you'll get this. This one, earlier on, I go and call it as H. You stick in the number, you get this one. Reference is always 1. So you iterate to 22 and 23. What is 22? You iterate 22 and 23, which means R is always equals to 1, starting from XF0 is 0.1.100, or F is already given, G is given, H is given. So this is 1. XF is this one. So you get K equal to 0, you get XF, K equal to 1, Y 1. If you do that Y1, you will get this answer. You get X1, XF1 here, then you put XF1 here, XF1 here, you get Y2, then you get this answer. Then after that, you get XF2, you put XF2 here, you get XF3, you put XF3 here, you get Y3, you get this answer. Then the main thing is that A is equal to the result in part B. You go and look at Y2 is 0.9543. Previous one, Y2 is also 0.943. You compare Y3, previous part is 10478. Here is also 10478. Okay, so you use the closed loop transfer function that include the observer and find y directly, or you go and iterate the states one bit by one bit, you will give you the same answer. This is just to make sure that all your algebra are connected. Okay, now go for a break. Come back at 7, then we continue. Okay, so the part D is to find the closed loop poles for the observer and the controller. So you basically use 2.44, it's just substitute numbers. You will then get this. And then you substitute numbers, you will get this. All right, you have to go and do yourself. Part E. Part E basically is like that. You see, up to now, how do you get your KOB? You get your KOB is by inventing W and V and say that R1 and R2 are given by 1000 and R2 is given by 0.1. From there, if you run the Kalman filter equation, you'll find the steady state Kalman filter is KOB is 0.6059 and 1.5093. That was how you find the KOB. Now, question E is such that, let's say you didn't use Kalman filter. Can you find KOB using pole placement? Yes, you can. So how? So we start with the pole. So let's say you decide now, you don't know KOB, you don't know. Now part E, assume that you don't know KOB. Part A to D, you got KOB from Kalman filter. All right, part E, assume that you don't have KOB. And then you choose your closed loop pole to be equals to this. All right, that's part E. You choose, like I explained to you before, closed loop poles actually determine your convergence rate of your estimation error. So you choose it to be this one. So from this one, from choosing the convergence rate, how you find KOB? Okay, this is how. You go and look at 244, which is the closed loop poles for your observer. 244 looks like that. All right, 244. You go and look at 244. Is determinant Zi minus AQBC. So 244. This is the closed loop poles, all right? 244. So this is 244. Just now was Zi A minus KOBC. All right, equals to 0. This is the determinant. You go and do the algebra, you will get this. The determinant of this is this. You got to go back and revise how you find the determinant of a matrix. So you will get this. Now, if the closed loop poles are like that, how you get this pole? It must come from this equation because this is the answer to this equation. Because if you equate to 0, z will be then equals to 0.1454 plus or minus j 0.2371, which is this one. All right. So you multiply this out, you must get this. Then you look at this equation and this equation, they must be the same equation. If they are the same equation, then you know that, oh, this z coefficient and z coefficient must be the same. So this must be the same as this. So, and then the constant term must be the same as the constant term. So you get these two equations here. And then two unknown, so you get your KOB is this one, which is the same KOB that you got in your part A to D. All right, so KOB now in part E is obtained from closed loop pole. From this closed loop pole, you go and get your KOB. From part A to D, the KOB, this same KOB was obtained from Kalman filter. It wasn't obtained from closed loop pole. It was obtained from Kalman filter. Then we go and find the closed loop pole. All right. Now, part E, we use the closed loop pole to get the KOB, which means this one you can specify, and from here you will get some KOB. Just to show you that you can get the KOB from the car that gives you the same one as the Kalman filter. Okay, now we go on to the next topic, and that is model predictive control with constraint. The keyword here is constraint. Constraint means what? Constraint means basically the limits. All right. So like if you have a power supply for a simple op-amp amplifier, the constraint of your output could be the voltage of your power supply. So if the power supply is 15 volts, then your op-amp circuit, even though your amplifier has a gain of, let's say, 5, you put in input is 2, output will be 10. Input is 1, output is 5. Input 3, output is 15. But your power supply is 15. So input 4, your output should be still 15 because it cannot be 20. Your power supply is 15. All right. So 15 will be the constraint of your output. All right. And in many rail systems, there are constraints. Let's say a valve to control the flow in a pipe. When the valve is fully open, the amount of fluid you can flow is at the limit. You open some more, you cannot increase beyond that. So that is your constraint. You can put in some more voltages into your valve. That's up to your calculation. Your MPC can calculate and say, I want to put in 10 volt, 20 volt, 50 volt. But if the valve at 10 volt is already fully open, you go and put 20 volt, it can't even open more than open. So that's it. All right. Of course, you can go in your maths, that's inside your computer. Use whatever formula you can calculate. You can always say output is 20 volt, but it's meaningless. But inside your calculation is 20, but the actual implementation is fixed at 10. So that's it. You have to take those things into consideration. If not, you will lose performance. And very often, it is not difficult to understand that you would like to operate near constraints at the upper limit. Why? Because in the first place, your processes is designed so that it operate near the constraint, then it is optimal. All right, basically, this is then it is most profitable or efficient. It's just like if this room is built for 100 students, then only 10 students come, it's not efficient. I will basically still use the same projector, the same energy to project. All right, the microphone switch on will still use the same power, only 10 people. Whereas if 100 people come in, I use the same amount of electrical energy to get the job done for 100 people. It's more efficient, more profitable. Okay, many things is not hard to imagine. So whatever we build, we like to more or less use it to the maximum or near the maximum. Okay, just like a bus. If the bus got 30 seats, we know the bus, every bus stop, we would like people get down, people come up, people get down, people come, to have more or less close to 30, 25 to 30. That's the best. But if every time the bus is practically empty, I lose money. All right. So most processes are designed such that it is best to operate near the constraint. Okay. Now, so in model predictive control, the control algorithm can take the constraint into consideration so that you're able to operate near or at the constraint and yet still be optimal. Like we will see through some examples. So now there are a few constraints that we want to discuss. Okay, the first constraint is your delta U, which is the delta U that you send the delta U that your MPC calculate. So you want to constrain such that your delta U is always less than some maximum value or less than some maximum value and greater than some minimum value. All right, the algorithm can calculate for you. So you have two inequality. So the way to do maths is that you break this up into two inequalities. So this one, you write it here. And then this one, you write it here. Okay, these two inequality is the same as these two inequality. And then we like to write things in matrix form. So these two inequality can be written like that. All right, you just multiply things out, you'll get back this. Now, then we can also consider constraint. Now, this is delta U, which means the change in the power. U is the actual power. This one I discussed very carefully when I first teach model predictive. U is the real power that your plant receive. This delta U is the power that your MPC calculate. All right. So the real power, you also want to have an upper limit and a lower limit. So to write, again, we're breaking this down into two parts. This is the same as this. And then this part is then the same as this. Okay. So we want to relate U to delta U. How? When we first started, this was how U is defined. All right, the real power is equals to the previous real power plus delta UK. All right, which means the MPC calculated power add on to the previous real power give you the current real power. Then if you iterate one sample, then it's quite standard. This you put inside here, then it will give you all right. So now you see, if you continue, you will find the pattern. All right, you can continue. UK plus 2 is equals to UK plus 1 plus and then you will put this inside here. Okay, so if you do this, you will find that U is actually UK plus delta U. So this is the first row. UK is UK minus 1 plus delta U. So this is what you get for your first row. Second row, UK plus 1. UK plus 1 is UK minus 1 plus delta UK plus delta UK plus 1. So you see, UK plus 1 is UK minus 1 plus these two, delta UK plus delta UK plus 1, which is this row here. All right. So, and so on. UK plus 2, if you put it inside, you will find that it is equals to this third row. Okay, you will see the pattern all the way down here. So once you see this pattern, we previously called this U, we call this C1, C2, delta U. Then you stick this in. You stick this in, you will find that this is this one here. All right. So C1 UK minus 1 plus C2 delta U. See, this one is U max. Okay, the first one is the same. You stick that in, you will get the first row. Then after that, you put this into matrix form, you will get this. All right, last constraint is output constraint. So output is also very practical. Let's say output is temperature. You definitely want to constrain it between a maximum and minimum. Obviously, it's maximum. Or if output is a level in a tank, your tank is only 1 meter, your Y must be less than or equal to 1 meter. If not, your tank will overflow. All right. If you are doing some temperature control, you may want to make sure your Y is less than, I don't know, some 150 degrees. If not, your chemical will, some unwanted reaction may take place or something like that, or things will burn or spoil, So having an output constraint is also quite common. This one, if you go and look, 212 says that this is actually calculated by this. All right. Then again, you rewrite this, you will get this. Okay, and then you rewrite this, you will get this. So you put this inside matrix, you will get this. All right, so now finally we got all this constraint, how you calculate the MPC. It is like that. The MPC is calculated to find delta U, which is the minimizes 23. All right, if you look at 23, which is this one, you go and look at 23. 23 is written like that. Okay. And so this is the MPC. MPC, we calculate delta U to minimize 23. You go back and look 23. No. So we minimize this. This is 23. And then from there we do, and then we get delta U. So delta U was obtained by minimizing 23. So there's MPC. But that time, we just minimize 23 and we stop there. Now, we add in constraint. All right, so now we add in constraint. So beside minimizing 23, which is the same as before, we add in subject to inequality constraint, this one. What is this one? All right, go back, which is all the constraints that we have discussed. So this matrix, we go and call it M1, and this we call it N1. So whatever is inside this matrix is M1, N1. Then whatever is inside this matrix, we call it M2, N2. Okay, then whatever is in this matrix, we call it M3, N3. All right, so which means now is subjected to this. We combine all the M1, M2, M3, N1, N2, N3 into this. So I just repeat for you before what is M1 is, just now I wrote for you the M1, M2, M3 is this, N1, N2, N3 is this. Okay. Now, in practice, in the industry, once you wrote it down this way, you will then use what we call this is what we call a standard quadratic programming problem. Means what? Means many numerical software like MATLAB, what we are very familiar with. You go and look at MATLAB, there's a function called quadratic program. All right, like that. Okay, they will ask you for input H, F, M, gamma. This is MATLAB programming. Then they will give you an output that is delta U and J. So means what? Means in practice, next time you go to work, you will then look at this, minimize this. All right. MATLAB will tell you minimize this. MATLAB call this H. Then MATLAB call this from here to here F. Then MATLAB will call this M. And MATLAB will call this gamma. So which means in your formulation, all you need to do, go and find phi transpose phi, R bar, you know, RS, F, and then all this you supply to MATLAB, M, gamma. MATLAB will give you what is, calculate for you what is delta U and what is the minimum J. That's what MATLAB will do. When MATLAB do this, MATLAB is doing this. It will minimize J and make sure at the same time it satisfies this constraint. That's what MATLAB will do. Okay? So you have to understand what MATLAB is doing. All right, MATLAB do the job for you, but you must know what has MATLAB done. So let's go through some example to see. You have to do it by pen and paper, then you will understand the results that you obtain from MATLAB. So let's look at one example. So in this simple example, this AP is 1, 1, 1. So that's easy. And then in model predictive control, you need to find the augmented plant. And I already gave you the formula for augmented plant A, B, C, and what is the augmented state X. So you use the 27, 25, go and find all this. All right. And the MPC here is a unit step input, so that's easy. Now, form the quadratic programming problem with constraint. The output must, or the K plus 1 and K plus 2 output must be less than Y max. So the first part is to find the MPC parameter. So that we have done before, so I will not go through it. You go and look at all this 21, 26, 20, 17, 18, that will give you this 4. Okay, put in the numbers. It will give you these 4 numbers. Then after that, let's say what is H? H is phi transpose phi plus R bar. Okay, phi transpose phi plus R bar. So you will have to find H. So phi is 1, 2. So phi transpose is 1, 2. R bar is 5. So this whole thing will be equals to 10. That's how you get 10 for H. Okay. Then F MATLAB say F is phi transpose RS minus FX. All right, minus phi transpose RS minus FX. So let me work it out for you. So F is phi transpose into RS minus F times Fx. So must be equals to phi is this one. So transpose is 1, 2. Okay. RS is 1, 1. So is 1, 1. F is this guy here. So is 1, 1, 2, 1. And X is X1K, X2K. Okay. So if you do that, you will then get this one here. Okay. So you got F. Then what is M? You see, you have to provide MATLAB with H, F. What is M? M, in our case, we just have Y max. So our M is just 5. All right, we don't have this one, don't have this one, don't have this one, don't have this one. So we just have 5. So M is just M3 and it's just 5. So M is 5 and our phi is 1, 2. So M is just 1, 2. What is gamma? We just have Y max. We go back and see, we just have this one. So this is our gamma. All right. Our gamma here, I wrote here, is N1, N2, N3. So N3 is just this one. We don't have the rest. So it's Y max minus Fx. So Y max minus Fx. So, and then what is F? F was 1, 1, 2, 1. So it's 1, 1, 2, 1. All right, X is X1, XK, X2K. So you stick everything in, you will get this. So now the quadratic programming problem you can give MATLAB what is H, what is delta U, sorry, what is H, what is F, what is M, what is gamma. Okay, so MATLAB will calculate the answer for you. Now let's see how MATLAB calculate the answer. If you stick in what is H, what is F into here, you will get this. You have to put the numbers inside. And then if you stick in this, you will get this. Okay, so part B, question B. So you have formulated ready. That is what MATLAB will do. You got all the H, F, M, and gamma. So that's done. MATLAB will solve the problem for you. So now we have to solve manually for ourselves. So now the question says, start with everything 0. The y max is 1, 1. So find x, delta x, yk. So now, how we solve? The first thing is the model predictive control without constraint is to minimize j. So our j is this one. So we do a delta j, dj, d delta k. So you differentiate this respect to delta k and equate to 0, you'll get delta k equals to this. Okay, this would be the MATLAB, no, sorry, not MATLAB, model predictive control without constraint. So this would be the value of delta u without constraint. Then k equal to 0, without constraint, this one gives delta u equals to 0.3. How come? Because when we start, everything is 0. So this is 0, this is 0, is 3 over 10. So it's 0.3. But you have constraint now. So constraint 20, where is constraint 20? Constraint 20 is here. So this is 0, this is 0. Constraint 10, 20 says that this is 1. The question give 1. So delta u must be less than 1. So constraint 20 give delta u less than 1. Constraint 21. So this is 0, this is 0. This is 1, there's a half here. Constraint 21 give you delta u must be less than 0.5. So now we have 3 numbers. You must find the 3 numbers. You choose between the smallest of 0.3, must be less than 0.1, must be less than 0.5. So the minimum of the 3 you can choose is delta u is 0.3. So the MATLAB will give you delta u equals to 0.3. What is happening? You see figure 3.1. Figure 3.1 show you the constraint delta u must be less than 1, must be less than 0.5, and minimum j is obtained at 0.3. Go and look at figure 21. It says that delta u must be less than 1, so this is delta u, so must be less than 1, so must be this one. You cannot be here. Another constraint says that delta u must be less than 0.5, so you must be here. You cannot be here. Minimum j says that delta u is 0.3. This is the j graph. So you see the minimum is here. So delta u. So which means as for k equal to 0, this delta u, we obtain 0.3, which satisfy the 2 constraints. And this is the minimum j that is obtained from the MPC calculation. Since it satisfies the constraint, so they will use the minimum j. So that's fine. Okay? Because you satisfy the constraint just says that you must be less than 0.5 or you must be less than 1. So the minimum j is obtained at 0.3. So, okay, we take the minimum j. We will not take 0.5 or we will not take 0.4. We will not take 0.2 because at 0.3, j is minimum. And MPC is to minimize j. So, of course, we'll take 0.3. That is clear. Let's look at the next sample. K1. K1, this was at 0.3, so we stick that in. All right. A and B is given. So you calculate, you will find x1 is 0.3. Then 22 give delta U is 0.06. 23 is the minimum J. 23, where is 23? Not 23. 22. All right, 22 is the minimum J. 22 because x is 0.3, you see. If this is 0.3, if this is 0.3, you calculate this, this will be 0.06. So minimum J is at 0.06. Constraint 20. Where is constraint 20? Give, now it's 0.3. So 1 minus 0.3 minus 0.3 is 0.4. So delta U must be less than 0.4. So that's why constraint 20 says must be less than 0.4. Constraint 21, you put 0.3 here, 0.3 here. There's a 1 here minus that, and then you halve it, says that it must be less than 0.05. So now you have three choices, 0.6, 0.4, or 0.05. So which means either this one, you choose this one, or you choose this one, or you choose this one. You choose the minimum of the three. The minimum of the three is 0.5. So delta U will be 0.5, 0.05. How come? Look at figure. Look at the figure. 3.2. If you look at figure 3.2, your minimum J is obtained here. But you have a constraint that says, you have two constraints. The two constraints says that it must be less than 0.4 and less than 0.05. Less than 0.4 means that it must be here. Less than 0.05 says that it must be here. At 0.06, you violate the constraint. All right, so you cannot. So you will have to choose 0.06. MATLAB will return you 0.06. That is the smallest J that satisfy the constraint at the same time. All right. 0.06 does not satisfy the constraint. 0.05 is the minimum J that satisfies the constraint. You can see from the curve. So MATLAB will do the calculation and return you an answer that say delta U1 is equals to 0.05. Okay, so that is the meaning of minimize J subject to the constraint. All right. Okay, then last part, if there are no constraint, how would things look like? So there's a part C, find Y if there are no constraint. Right now, up to now, I say Y got a Y max of 1, which means Y is constrained to 1. If there's no constraint, then the OMPC works. So you go and look at 30 and 31, you will get KR and KMPC. Then you go and look at 34, you find that Y, the transfer function is like that. All right, you have to go back. This, I can't teach really. You go and substitute into 34, you will get this. Then you will get this. Okay, then you find Y0. This is 0, this is 0, this is 0. So Y0 is 0. I gave it to you. Y1, this will be 0, this is 0. This is 1. So Y1 is 0.3. So you get 0.3. Y2, since this is 0.3, this is 0, this is 1, you will get 0.66. Okay, go and iterate this for yourself. I gave you the answer here. So you get all your y for k equal to 0 to 9. Then you plot this out. You see figure 3.3. You see, this is part C. Part B, though I work out a few for you, I just do the detail for you 1, 0, 1. But if you continue, you work hard, you continue the same step, huh? No point, writing it out. Once you know how to do k equal to 0, k equal to 1, you just iterate k equal to 2, 3, 4. If you iterate, you will get this answer here. This will be your y. So if you plot it out, this is part B. All right, it is clear. Y max is 1. Part C, no constraint, so it will overshoot 1. Part B, because we use a MPC subject to a constraint of y max equals to 1, you find that your y will always be less than or equals to 1. Okay, all right, I will stop here for tonight. So I won't see you next Friday. I'll see you next Friday.